Welcome to the first session of the Generalized Method of Moments lecture. And to start, we will talk about a couple of math concepts. In particular, let's talk about what constitutes orthogonal vectors. So let's suppose that we have two vectors, x and z, and they are orthogonal, indicated by this kind of upside down t symbol. So over here we say x is orthogonal to z, if and only if the inner product of x and z is equal to 0. This is the dot product of the vectors. So to see that this would be the case, also notice that the definition of the cosine of the angle between vectors is the dot product of x and z divided by the length of x and z. Well, the cosine of 90 degrees, if you look it up, is equal to 0. And the way that that could be the case for all non-zero x's and z's is going to be if x transpose z itself is equal to 0. So this is just another way to see that variables have a 90-degree angle between them if they are orthogonal, and therefore if x transpose z is equal to 0. We say that a vector, in this case I'll denote A, is the basis for a whole set of vectors if we consider that the set of vectors A star are all of those vectors that are the vector A multiplied by some constant on the real line. It can be both negative or positive. And this would define A as the basis for a one-dimensional space. So if we think of this vector here as A, and if I can multiply it by any constant, lambda, on the real line, positive or negative, I can create new vectors that follow anywhere up to infinity in either direction. So it basically will define a space of possible vectors as a single line that matches the kind of direction or orientation of the original A. So A is the basis for a one-dimensional vector space. Two vectors, A and B, constitute the basis for a set of vectors, A star, that will be any linear combination of A and B. So now I got my lambda sub A, lambda sub B as two constants anywhere on the real line, and a linear combination of those, any linear combination of those, will constitute some vector A star, and the whole set of A stars that you get is a two-dimensional space. So notice that we have here two vectors A and B. Through taking linear combinations of these, I can essentially get any vector all the way around in any direction of the plane that these two vectors fall in. So A and B, if you were to draw them in the air, you would be able to fit a plane through them, and that plane going in infinitely many, in infinite distance, essentially, in any direction, according to that plane, sets up a two-dimensional space, and that includes all of the vectors A star. Now, there's something to note here, and that is this is only the case if A and B do not land on top of each other, right? If this were A instead, well, now this A and B would not at all describe a two-dimensional space. It would, in fact, describe just a one-dimensional space, because A would equal to some constant of B. So when that is not the case, these two, A and B, will create the basis, or are the basis, for a two-dimensional space. For that not to be the case, or when that is not to be the case, the determinant of AB as think of it as a matrix, the vector A as a column here, and the vector B as a column. Take that, transpose times it again. The determinant of that should not be equal to 0. We can continue to extend this. So now we can have three vectors that constitute the basis for a three-dimensional space, such that the linear combination of the three can bring about a whole set of possible vectors A star, and such that the matrix where M is going to equal to A, B, C as a matrix where this is a column, this is a column, this is a column, the determinant is not equal to 0. If it turns out that one of these, let's say for example, instead of what we see here of A, B, and C, let's suppose C was itself actually a linear combination of A and B, so it is not actually this one here, then we actually have a two-dimensional space with 3 vectors, right? And that's going to generate the determinant actually equal to 0, and that is one way to determine whether or not the set of vectors constitutes the basis for the number of dimensions that correspond to the number of vectors. In this case, it would not be, because some linear combination, lambda 1a plus lambda 2b, would equal to c. So really there's a two-dimensional space in what I drew here. Now, if two vectors, x transpose y, are equal to 0, so they're orthogonal to each other, and then another vector z transpose y is also equal to 0. So y is orthogonal to x, and y is orthogonal to z. Then y will be orthogonal to any linear combination of x and z, which basically means that y is orthogonal to the vector space defined by x and z as a basis. This is x, and this is z. It defines a whole two-dimensional vector space. I'm drawing here as a finite one, but in fact it goes off infinitely long as a plane that goes between the two, z and x, or that captures both z and x. And then if we take a vector y that is orthogonal to both x, didn't mean to do that, hang on, put that back. There's my z. That is orthogonal to both z and to x, then it's orthogonal to really any vector in the plane defined by z and x. That's basically what this is saying. Y is orthogonal to the vector space defined by x and z as a basis. We can also talk about orthogonal subspaces. So let's let a full kind of vector space W be what we would consider as a subspace X cross subspace Z. You'll see what that means in a little bit. But these two subspaces, X and Z, are considered orthogonal if for all vectors in the X space and all vectors in the Z space, each vector is orthogonal to each other. X is the orthogonal complement of Z in terms of the spaces. These should be capitalized here in terms of the spaces x and z. If all of the vectors, basically if this definition holds, if for all x and z they are orthogonal. So let's consider a two-dimensional space, and we have 2 dimensions as described in this first graph. And if I were to have any vector in the first space, it will be orthogonal to any vector in the second space. Okay. So we have the space defined by vector, let's say A, is orthogonal to the space defined by vector B. So essentially this line here and this line here constitute 2 orthogonal subspaces of the overall two-dimensional space. This one, which maybe I'll call B, this one I'll call A. As far as the line goes, B is the orthogonal complement of A. Even if I were to have, let's look at the second second graph over here, even if I were to have vectors that don't fall exactly on the axes like I did in the first, instead I've got a vector here, A, and a vector here, B, then A defines a one-dimensional space, B defines a one-dimensional space. All the B's are orthogonal to all the A's, so A and B are orthogonal complements that define together make up the full two-dimensional space. So it doesn't have to be that the vectors line up on, like the first graph here, they don't have to line up on the axis, so to speak. Same thing could apply here. Let's say I've got axis, this way I'll just call them dimensions 1, 2, and 3, or axes 1, 2, and 3. And it might be that I am looking at a couple of vectors that fall in this 2, 3 plane, right, all the way around on the 2, 3 plane. So these vectors, A, B, make up the basis for a two-dimensional plane that comprise all of the vectors that could be plotted on the 2, 3 dimension here, which means the orthogonal complement of that is going to be this one-dimensional space that goes along this first dimension here. So the two-dimensional space, comprising basically 2 and 3, is the orthogonal complement of the one-dimensional space defined by this dimension 1. Now, we say that X is orthogonal to Z in terms of the spaces themselves if it's the case that a basis in X, this is a set of vectors, is orthogonal to a basis in Z. And this is true for any basis. Okay, so the necessary condition for that to be the case is that for all vectors, X and Z, if X is correlated, if X is orthogonal to Z, then the basis X is orthogonal to the basis Z. Now you notice that X being orthogonal to Z means that X transpose Z is equal to 0. But X, being a vector in the space defined by the basis vector X naught, can be looked at as simply a constant times that vector, and similarly for Z. So we can rewrite X transpose Z as AX naught transpose B naught, Z naught B, and that's equal to 0 only if the two sets of bases are themselves orthogonal, assuming that A and B themselves are not 0. We're not talking about zero vectors here. Similarly, since of the sufficient conditions for all bases X and Z and all of the vectors X and Z, if the bases are orthogonal, then all the vectors are orthogonal. If the bases are orthogonal, then of course their inner product is equal to 0, and therefore essentially any linear combination or scale or any constant times X star X naught transpose a constant times Z naught is also 0. But there exists a constant for all X such that X is equal to A naught, X naught A, and there exists some constant B for all Z such that Z is equal to the basis Z naught times B. Therefore, if the two bases are orthogonal, then so are X and Z for all X and Z. Now let's talk about projections. Now in this case, what we're thinking of is putting these concepts of orthogonal sets together. So here is for all vectors X in a vector space X and all Z's in the vector space Z, then we can describe a vector W as equal to the sum of X and Z. such that the space that you can think of it as W is an element of as a vector is equal to the product of X and Z, the two X spaces, two orthogonal spaces. Well, I guess we didn't specify they're orthogonal at the moment, but the two spaces. And what this is to say that X and Z are then projections of W onto, the vectors X and Z are projections of W onto the subspaces X and Z. Think of the two dimensions here. Let's suppose that the x-axis here, so all vectors that go along in this direction, are this particular space X, right? And all of them that go along in the up-down direction are part of this space Z. We can take and we consider W then as equaling to the ZX product, so it's the full two-dimensional space, then any vector W can be described as being equal to a vector in the X space, being this little x, and a vector of the Z space, being this little z, X plus Z, which is to say that there exists an X and there exists a Z such that W is equal to X plus Z. X and Z are the projections of W onto the subspaces of X and Z. Let's take a linear regression example. So let's plot out three dimensions, N1, N2, and N3. My N2 is meant to be 90 degrees. I'm just looking at an angle so that it's looking like it's not. I'm trying to do 3 dimensions on 2 dimensions here, so these are all 90 degrees from each other. So n equal to 1, n equal to 2, and n equal to 3. You can think of this as actually a sample size. Each observation, three observations are going to be used. In the first observation is n equal to 1, the second n equal to 2, and third n equal to 3. Well, I can measure a variable x, and it can be plotted in this three-dimensional space, right? Let's say it's age. Well, there's a certain age for the first observation, a certain age for the second, and a certain age for the third. So here is my x variable. I can do the same thing with z, and I can plot a variable z. And then I can plot a third variable y. Now, if I take the x and z as a basis, so x and z as a basis, is the basis for a two-dimensional plane. This is my dashed plane here to represent the two-dimensional plane, although we must understand that this actually goes out infinitely far, but just to be able to show it. So that plane goes right through both z and x, right? Or z and x are both in that plane. So all vectors in this plane, no matter where you look, are constituted a linear combination of z and x. This is overall a three-dimensional space. So a two-dimensional space must have an orthogonal complement to it that makes up the three-dimensional space. And sure enough, we have the one leftover dimension, this orthogonal complement of x and z, where we could think of that dimension as being 90 degrees to the plane. So now, if I were to plot my y vector in this three-dimensional space, right? We have three observations of y, so I can plot the y for n1, the y for n2, and the y for n3. I can say that y is going to equal to a sum of a vector in the orthogonal complement and a vector in the two-dimensional space. So my ax plus bz is the vector, the linear combination in this plane, plus what I'll call e is the vector in the orthogonal complement of that plane. And y is equal to the sum of the two. This is actually a graphical representation of ordinary least squares. And you can break it down into looking at orthogonal complements of a space defined in terms of the number of observations. Another concept to remember is what constitutes a positive definite matrix. So some matrix M is positive and definite if, for all non-zero vectors x transpose mx is greater than 0, and for all x equal to 0, which is to basically say when x is equal to 0, x transpose m is in fact then equal to 0. This means that x transpose x is 0 only at x equals to 0. We will use this construction as the basis to get the solutions that we want in generalized method of moments. Basically, you could think of this is if I wanted to minimize this quadratic, it has only one minimum, and that is at x equal to 0. If x is not equal to 0, then it is strictly greater than 0. So to minimize this quadratic, it again must be the fact that x is equal to 0. We're going to take advantage of that fact in our generalized method of moments. One more thing, though, to remember, and that is that with systems of equations, if there exists a unique solution, then in p unknowns, we can solve them from p independent equations, right? As, say, equations that provide p sources of information. If you have more than p sources of information, you essentially only use p sources of information in order to solve the problem. If you have less than p sources of information, then you can't solve for all p unknowns. That's just kind of the basic rules associated with systems of equations and solving their the number of parameters and number of equations.